Hi, this video follows from both the discussions on real numbers and on sequences. In the last video on overview of real numbers, we used the term fillers over the set of rationals, but we did not talk on what they really are and how to get them. And what difference does it make being present? What are the differences between the sets of rationals and reals? Today, we will look at them. Hey, Patty used the term fillers in the discussion with Miss Green. They said they're not completely understood by digits in decimal representation. Then how to get them? Okay, let's speak on that. You know sequences? Patty spoke with Faye on that. Yes. Now let's see. Can you write down what square root of 2 exactly is, or just describe it with decimal representation? I have never tried. Okay, that's fine. But it is actually true that you cannot write root 2 completely or describe it with digits in decimal representation with a repeating sequence of digits. Why so? Okay, if you write or describe with repeating bunch of digits, that is, a cycle, then if the only digit repeating is 0, then you clearly get a rational. If it is not just 0, then can you say something about it? You said you know sequences. Yes. Considering the decimal part of the number where the repetition occurs, it is a geometric series of number, certainly of ratio with modulus less than 1. And the formula of GP series tells me that it is a rational number. I am using GP series for rationals. That series is simply a rational sequence, and I can use the idea because it doesn't use anything else than rationals. On the other hand, if I assume square root to be a rational number, I end up with an impossibility. Okay, now I understand that there are numbers that have no describable representation through digits. What next? Now look. If you take the number square root of 2 and try to see the decimal representation, you can know up to whatever term you like by computation, but you can never know all the terms, that is, digits at the decimal places, right? Right, so it makes sense to make sequences like 1.414, 1.4142, 1.41422135, 1.4142135623, and so on. And by definition of square root 2 and the idea of convergence, we say that this sequence converges to square root 2. Can we this way describe all the fillers? Yes, you are close. But we have to generalize this to all possibilities. To get all the fillers, we would not use the idea of convergence. Why, you know? Yes, because there we have to first tell limit. And we are yet to know them. Right, so here we bring a concept. We by now have only rationals in hand, so the concept is about rational Cauchy sequence. For every positive rational k, there is some tail of the sequence which is in between two rationals at a distance of k. Rational sequence with this property is called Cauchy. By our definition, convergent rational sequences are definitely Cauchy. Now we associate a symbol to each Cauchy sequence, calling them real numbers. But the rule is only equivalent Cauchy sequences are associated to the same real number. What are they? If we fix an arbitrary rationality as small as we like, then the tails of the two sequences from some nth term sit in between two rational numbers at distance d. Now these are looking so mysterious. How would I treat them as numbers? How to do algebra on them? We define them by term-wise operations whenever possible. Like in addition, multiplication, they are easy. But in reciprocation, we need the Cauchy sequence to be bounded away from 0. That is, there should be a positive rational k so that the terms of the rational sequence are either greater than k or less than minus k, is it? Yes, and the fun is we have such a sequence associated to any non-zero real number. Okay, but where are my rationals? Right now numbers are looking like classes of equivalent Cauchy sequences. They indeed are, and don't worry for your rationals. We embed them in those classes by the numbers associated to the constant rational sequences. This actually turns out to be consistent with the algebra that we imposed. Okay, then how do I get to know that those real numbers are the real numbers that I know about? Precisely, how would I know the order? They are just mysterious numbers that people have created. We have ordering for rationals, but for the mysterious objects? Yes, for that we have an idea. The idea of positive and negative. If a sequence has its tail bounded away from 0, then we call the associated number to be positive. Similarly for negative. Now the idea of ordering comes. If x minus y is positive, then and only then x is greater than y. These actually come down to if there are two rational Cauchy sequences, an and bn, such that they have their terms like this: an is less or equal to bn for every n, then the real numbers a and b associated to them respectively have the relation a less or equal to b. Okay. Now something interesting happens. You have ordering and you have Cauchy sequences. You can define supremum. We will define it with Cauchy sequences very easily, with ordering in hand. True. This way your real numbers are formed. All the rationals are embedded in there. It has ordering and it is complete. We may talk on how to prove the existence of supremum if you like. Also, this idea of Cauchy sequence is not meaningless. You can prove that they are convergent and they converge to those mysterious real numbers. Okay, now this has the supremum property that rationals did not have, right? Yes, you are right. And these real numbers, which are not rationals, are the fillers for the gaps in rationals. And they are irrationals. So this is how fillers were born, and it lived happily ever after. Thanks for watching. Stay tuned.